Look up at the night sky. What do you see? Stars, countless stars, twinkling in the darkness. They're more than just pretty lights. Stars are the engines of the cosmos. Without stars, we wouldn't exist. Stars have captivated humanity for millennia. They use stars to navigate and inspired myths and scientific curiosity, yet they still hold many mysteries. Stars come in many forms. Some are massive and blazing hot. Some live for billions of years, others burn out in millions. Join us as we explore the life of stars from birth to death. We're about to embark on a stellar adventure. At its core, a star is a giant ball of gas, mostly hydrogen, with a dash of helium. But what makes it shine? The answer lies deep within nuclear fusion. This process is the heart of every star, keeping them burning for millions or billions of years. Imagine squeezing atoms together so tightly that they fuse. That's what happens in a star's core. The immense pressure and heat force hydrogen atoms to combine, forming helium and releasing energy. This energy travels outward, eventually reaching the star's surface, released as light and heat. The conditions needed for fusion are extreme, millions of degrees and unimaginable pressure. Stars are in a constant battle with gravity. The outward pressure from fusion pushes against the inward pull of gravity. This balance keeps a star stable for most of its life. When the balance shifts, the star changes. This dance between fusion and gravity drives the entire life cycle of stars. It's a cosmic ballet that's been playing out for billions of years. Stars aren't born in isolation. They come to life in vast cosmic clouds called nebulae, made of gas and dust. Think of them as stellar nurseries. Here, the ingredients for new stars slowly gather and condense. It all starts with a disturbance, maybe a shock wave from a nearby supernova, or the gravitational pull of a passing galaxy. This causes parts of the nebula to collapse, breaking into smaller clumps. Each clump could become a star or even a system of stars. As a clump collapses, it spins faster, like an ice skater pulling in their arms. The center gets denser and hotter, becoming a protostar. This is the embryo of a star, but it's not shining yet. The protostar continues to grow, gobbling up more material from its surroundings. Finally, when conditions are just right, fusion begins. The protostar ignites, and a new star is born. This process isn't quick. It can take hundreds of thousands of years. The leftover material might form planets. This is how solar systems like ours are born. Every star you see was once a baby in a cosmic cradle. Once a star ignites, it enters the main sequence, the star's adult life where it spends most of its existence. Our Sun is a main sequence star in perfect balance with fusion pressure matching gravity. It steadily burns hydrogen, converting it to helium. Main sequence stars vary in size and color. The smallest are red dwarfs and the largest are blue giants. Our Sun is a yellow dwarf. The life of a main sequence star is steady but changing. It uses up hydrogen fuel, leading to big changes as it nears its end. As a star ages, it undergoes dramatic changes. The hydrogen in its core starts to run out, marking the end of its main sequence life. For stars like our Sun, the next phase is the red giant stage, a time of great expansion and cooling. The extra energy causes the star's outer layers to expand dramatically, ballooning to hundreds of times its original size. Despite this growth, it actually cools down, giving it a reddish hue. Mercury and Venus will be engulfed. Earth might survive, but it will be a scorched, lifeless world. This won't happen for billions of years, but it shows the powerful influence stars have on their surroundings. Stars are cosmic cookpots where the elements of the universe are forged, a process called nucleosynthesis. Without it, the universe would be nothing but hydrogen and helium. The fusion process in stars is like a cosmic game of element building, starting with hydrogen fusing into helium. In more massive stars, the process doesn't stop there. As the core temperature rises, helium can fuse into carbon, then carbon into oxygen, neon, and so on. Each step requires higher temperatures and pressures, like climbing a ladder of element creation. The most massive stars can create elements as heavy as iron in their cores. But iron is where the process stops, as fusing iron doesn't release energy. This element-building process is why we exist. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in stars. When we look at the night sky, we're seeing the factories that made us. As Carl Sagan famously said, we are made of star stuff. It's a poetic truth rooted in stellar physics. All stars must die. It's an inevitable part of stellar evolution, but not all stars die the same way. The star's mass determines its fate, the deciding factor in how dramatic its end will be. Some stars go out with a whimper, others with a bang. For stars like our Sun, the end is relatively peaceful. After the red giant phase, they shed their outer layers, forming a beautiful planetary nebula. The core that's left behind becomes a white dwarf, small, dense, and slowly cooling over billions of years. More massive stars meet a more violent end. When they can no longer sustain fusion, they collapse, triggering a massive explosion called a supernova. It's one of the most energetic events in the universe, briefly outshining an entire galaxy and spreading heavy elements far into space. The aftermath of a supernova depends on the star's original mass. Some leave behind a neutron star incredibly dense. A teaspoon would weigh billions of tons. The most massive stars collapse into black holes, regions where gravity is so strong not even light can escape. They're the most extreme objects in the universe. White dwarfs are the quiet retirement homes of the stellar world. What's left after a low or medium mass star sheds its outer layers. Our Sun will become a white dwarf in about 5 billion years. These objects are fascinating in their own right. A white dwarf is incredibly dense, like squeezing the mass of the Sun into a ball the size of Earth. They're so dense that the electrons in their atoms are squished together, creating a state of matter called degenerate matter. Despite their small size, white dwarfs can be incredibly hot. A newly formed white dwarf might have a surface temperature of 50,000 degrees Celsius, but they have no way to generate new heat and slowly cool over billions of years. White dwarfs tell us a lot about the history of our galaxy. They're like cosmic fossils. By studying them, we can learn about star formation rates in the past and measure the age of star clusters. In a way, they're the timekeepers of the universe. Supernovae are the grand finales of the stellar world, explosions of cosmic proportions. A single supernova can outshine an entire galaxy. It's nature's most impressive fireworks display. But it's more than just a light show. Supernovae play a crucial role in the universe. There are two main types of supernovae. Type Ia occurs in binary star systems, when a white dwarf pulls matter from its companion star and explodes. Type 2 supernovae occur when massive stars collapse at the end of their lives. Both types release enormous amounts of energy. Supernovae are cosmic recycling centers, spreading heavy elements throughout space. These elements become the building blocks for new stars, planets, and even life. The iron in your blood was likely forged in a supernova explosion billions of years ago. We are quite literally made of stardust. Studying supernovae helps us understand the universe. They act as standard candles for measuring cosmic distances. This led to the discovery that the universe is expanding at an accelerating rate, revolutionizing our understanding of cosmology. When massive stars die, they leave behind some of the strangest objects in the universe, neutron stars and black holes. These are the exotic endpoints of stellar evolution, pushing the limits of physics as we know it. Neutron stars form when a star between 8 and 20 times the mass of our Sun explodes, and the core collapses, crushing protons and electrons into neutrons. The result is incredibly dense. A neutron star the size of a city could have the mass of the Sun. They spin rapidly, sometimes hundreds of times per second. Black holes form from even more massive stars. When these giants collapse, gravity wins completely. The core is crushed beyond the neutron star stage, becoming a singularity, a point of infinite density. Nothing, not even light, can escape its gravitational pull. The boundary of no return is called the event horizon. These objects have extreme effects on their surroundings. Neutron stars can have magnetic fields trillions of times stronger than Earth's. Black holes can tear apart stars and shape entire galaxies. They're not just the graveyards of stars, they're active players in cosmic evolution. Studying them gives us insights into fundamental physics. The story of stars doesn't end with their death. It's part of a greater cosmic cycle. Materials from dead stars become building blocks for new ones. This cycle enriches the universe with heavy elements. Stars release their material back into space. This happens gently or violently. Enriched clouds collapse to form new stars. Each generation has more heavy elements. The first stars created heavy elements. Enough elements formed rocky planets and life. Stars are born, live, and die. We are children of the stars.